Preparing for a Grafana Backend Engineer interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you design a backend service that serves dashboard queries across Prometheus, Loki, and SQL data sources? I would put a query orchestration layer behind a stable HTTP or gRPC API. It validates requests, checks tenant permissions, translates the query for each data source, and executes independent requests concurrently with bounded workers. Each downstream call gets a deadline, cancellation, and normalized error handling. I would add caching for safe repeated ranges and metrics for latency, failures, and fan-out. The design should return partial results only when the API contract makes that behavior explicit. While answering, focus on API boundaries, data source abstraction, query translation, concurrency, timeouts, partial failures, caching, authorization, and preserving consistent response formats across heterogeneous systems. Question 2. Why is Go a strong choice for Grafana backend services, and what Go practices would you apply? Go fits backend infrastructure because it offers fast compilation, predictable deployment, strong networking libraries, and lightweight concurrency. I use context for deadlines and cancellation, small interfaces at dependency boundaries, wrapped errors with useful causes, and bounded Go routines rather than launching work indefinitely. I also run race detection, benchmarks, pprofessor, and static analysis in C. I prefer straightforward code over abstraction-heavy designs, because operational clarity matters in long-lived platform services. Make sure to cover Go routines, channels, context cancellation, interfaces, explicit errors, memory safety, profiling, dependency management, and avoiding unbounded concurrency or overly clever abstractions. Question 3. How would you prevent a Grafana backend API from becoming a bottleneck during a traffic spike? The problem is usually overload amplification. One dashboard request can trigger many expensive data source queries. I would enforce per user and per tenant limits, bound fan-out, apply deadlines, and shed work before queues grow uncontrollably. Stateless API instances can scale horizontally behind a load balancer, while caches absorb repeated queries. I would size database pools deliberately and expose saturation metrics. Load tests should validate behavior under spikes, especially whether latency degrades gracefully instead of exhausting every dependency. In your answer, talk about load shedding, rate limits, horizontal scaling, connection pools, caching, queuing, backpressure, database protection, latency budgets, and capacity-based observability. Question 4. How would you implement multi-tenancy and tenant isolation in a Grafana-like backend? I would derive tenant identity from authenticated claims, never from an untrusted request parameter alone, then pass it through every service and repository call. Queries, cache keys, background jobs, and audit events must include tenant scope. Database access should enforce tenant predicates centrally, with stronger isolation for sensitive deployments. I would add quotas for dashboards, alerts, query duration, and storage. Tests should deliberately attempt cross-tenant reads, cache collisions, and forged asynchronous messages. Be sure to mention tenant identity propagation, authorization checks, database scoping, cache keys, resource quotas, isolation boundaries, auditability, and preventing cross-tenant leakage in logs and asynchronous jobs. Question 5. How would you design an alerting scheduler that remains reliable during restarts and high evaluation volume? I would separate rule definitions, evaluation scheduling, and notification delivery. Definitions and evaluation state belong in durable storage, while workers claim do rules using leases or a leader-coordinated schedule. Evaluations need deadlines, bounded concurrency, and explicit handling for missed intervals after restarts. Notification delivery should be idempotent, with deduplication keys and retry policies that avoid storms. I would expose scheduler lag, evaluation duration, failures, and notification backlog so operators can detect degradation quickly. Focus on durable state, scheduling semantics, leader election, idempotency, missed evaluations, concurrency limits, retries, notification deduplication, clock handling, and operational visibility. Question 6. What caching strategy would you use for dashboard and data source queries? I would cache only requests whose results are safe to reuse, using a key-containing tenant, data source, query, time range, variables, permissions, and relevant configuration. Time ranges can be normalized when that does not change semantics. TTLs should reflect freshness requirements, and cache size needs eviction and tenant-aware limits. Request coalescing prevents a stampede when many panels miss simultaneously. I would bypass caching for highly volatile or permission-sensitive queries unless the contract is unambiguous. While answering, cover cache key design, tenant and user dimensions, time range normalization, TTLs, invalidation, stale data, stampede prevention, memory limits, and deciding when caching is unsafe. Question 7. How would you evolve a public backend API without breaking existing Grafana clients or plugins? I start by treating existing clients as part of the contract. Additive fields and endpoints are safer than changing meanings or removing fields. For incompatible behavior, I introduce a versioned root or negotiated capability, then support both paths during migration. Contract tests should cover old and new clients, including malformed input. I would instrument usage of deprecated fields, publish a timeline, and provide migration examples. Compatibility is not just syntax. Defaults, errors, pagination, and authorization behavior matter too. Mention versioning, backward compatible schema changes, tolerant readers, deprecation policy, contract tests, migration paths, feature flags, observability, and communicating behavior changes to plugin authors. Question 8. How would you secure Grafana backend endpoints and data source credentials? I would authenticate every request, authorize against tenant, organization, resource, and action, and enforce checks server-side rather than trusting the UI. Data source credentials should be encrypted at rest, redacted from logs, and exposed only to narrowly scoped connection code. Proxy endpoints require SSRF defenses, allo lists, DNS and redirect validation, and strict timeouts. Inputs need size and type limits, while errors avoid leaking credentials or infrastructure details. Security tests should include privilege escalation and tenant isolation cases. Be sure to discuss authentication, authorization, secret storage, encryption in transit and at rest, SSRF protection, input validation, audit logs, least privilege, and secure error responses. Question 9. How would you handle partial failures when a dashboard queries multiple data sources? I would execute independent panel queries concurrently but isolate each with its own timeout and cancellation path. Errors should distinguish invalid queries, authorization failures, timeouts, and dependency outages. The response can include successful panels plus structured errors when the product permits partial rendering. I would retry only transient failures, with jitter and strict limits. Retries on overloaded systems are dangerous. Metrics and traces should identify the failing data source, tenant, query class, and downstream latency. In your answer, cover independent deadlines, cancellation, error classification, partial result semantics, retries, fallback behavior, user visible diagnostics, and avoiding retries that amplify downstream outages. Question 10. What database design considerations matter for Grafana metadata such as dashboards, folders, users, and alert rules? For metadata, I would usually choose a relational database because dashboards, permissions, folders, and alert rules have strong relationships and transactional requirements. Tables should include tenant scope, stable identifiers, timestamps, and carefully chosen unique constraints. Indexes should follow actual lookup patterns, such as folder ownership or dashboard UID. Updates can use optimistic locking to prevent silent overwrites. Migrations must be backward compatible, observable, and reversible where practical, with large data changes performed incrementally. Focus on relational modeling, indexes, transaction boundaries, optimistic locking, migrations, uniqueness, soft deletion, tenant scoping, query patterns, and handling concurrent updates safely. Question 11. How would you implement idempotency for dashboard updates, alert evaluations, or webhook delivery? Idempotency means repeating an operation produces the same intended result rather than duplicating side effects. I would accept a client or event identifier, store it with the operation outcome, and enforce uniqueness transactionally. For webhook delivery, the recipient should also receive a stable event ID because network failures make acknowledgement ambiguous. Records need retention limits and status transitions such as pending, succeeded, or failed. I would document which operations are idempotent and detect conflicting payloads for reused keys. Make sure to cover idempotency keys, durable deduplication records, atomic rights, retry semantics, request identity, expiration, side effects, and distinguishing safe retries from conflicting operations. Question 12. How would you design observability for a Grafana backend service itself? I would instrument request rate, errors, duration, saturation, dependency latency, queue depth, and resource usage. Structured logs should include a request or trace ID, operation, tenant safe context, and error cause without secrets. Distributed tracing is especially valuable for dashboard fan-out into multiple data sources. Labels must avoid unbounded values such as raw queries or user IDs. Alerts should reflect user impact and sustained symptoms, while exemplars can connect latency metrics to representative traces during investigation. Discuss structured logs, metrics, distributed traces, correlation IDs, RED or use signals, tenant-safe labels, exemplars, alert thresholds, and avoiding high cardinality or sensitive telemetry. Question 13. How would you test a Go backend that integrates with several external data sources? I would keep business logic testable with small interfaces, then use focused unit tests for validation, authorization, retries, and response normalization. Contract tests verify assumptions against each supported data source, while integration tests exercise real containers or controlled environments. I would inject clocks, randomness, and transports so timeout and retry behavior is deterministic. Failure injection should cover slow, malformed, and unavailable dependencies. C should run race detection, benchmarks, static analysis, and selected end-to-end scenarios. In your answer, cover unit tests, contract tests, integration environments, fakes versus mocks, failure injection, race detection, property testing, performance tests, and deterministic time control. Question 14. How would you manage concurrency and cancellation in a Go service handling many dashboard queries? I would propagate the incoming context to every downstream operation and derive shorter deadlines where appropriate. An ERR group like coordinator can cancel sibling work when failure makes the overall result useless. Fan-out must use a semaphore or worker pool, otherwise one request can create unbounded Go routines and connections. Channels should have clear ownership and closure rules, while shared state requires synchronization or immutable snapshots. I would test cancellation, client disconnects, blocked dependencies, and Go routine counts under sustained load. Focus on context propagation, bounded worker pools, ERR group-style coordination, channel ownership, avoiding Go routine leaks, shared state synchronization, deadlines, and measuring queue or execution pressure. Question 15. How would you build a reliable background job system for exports, provisioning, or alert notifications? I would persist jobs before acknowledging the triggering request, then let workers claim them with leases or visibility timeouts. Each job needs an idempotency key, bounded retries with exponential backoff, and a dead letter path for operator inspection. Priorities and per tenant limits prevent one customer from monopolizing workers. Graceful shutdown stops new claims and finishes or releases active work. Important metrics include queue depth, oldest job age, attempt count, success rate, and processing latency. Mention durable queues, visibility timeouts, work releases, retries with backoff, dead letter handling, idempotency, prioritization, rate limits, graceful shutdown, and monitoring job age. Question 16. How would you design a plugin or data source integration boundary that remains maintainable over time? I would define a narrow interface around query execution, health checks, configuration validation, and capabilities. The core service owns authentication, deadlines, limits, tracing, and common error translation. Plugins own protocol-specific translation. Capability negotiation prevents the core from assuming unsupported features. Versioned contracts and compatibility tests protect existing integrations. Plugin failures must not crash the host or bypass tenant controls. Keeping the boundary small makes new data sources easier to add without contaminating shared backend logic. Be sure to cover stable interfaces, capability negotiation, validation, version compatibility, timeout ownership, resource limits, error contracts, documentation, and isolation between plugin-specific behavior and core services. Question 17. How would you approach a zero-downtime deployment involving schema and backend changes? I would use expand and contract. First, add nullable columns, new tables, or indexes without requiring old binaries to change. Next, deploy code that can read both representations and write the new one, backfill asynchronously, then switch reads behind a feature flag. After verifying metrics, remove legacy behavior in a later release. Instances need readiness checks, connection draining, and graceful shutdown. Rollback planning must account for irreversible data transformations, not just binary replacement. Focus on expand and contract migrations, backward compatible binaries, rollout sequencing, feature flags, health checks, rollback limits, connection draining, and verifying behavior with real traffic metrics. Question 18. A dashboard query suddenly causes high CPU and database load. How would you investigate and mitigate it? First, I would confirm whether the issue is isolated to one tenant, query shape, endpoint, or deployment using latency, CPU, database, and trace data. I would inspect query plans and profiles for missing indexes, excessive cardinality, repeated calls, or an accidental unbounded range. Immediate mitigation could include rate limiting, disabling a feature flag, canceling expensive work, or rolling back. Then I would add query limits, regression tests, dashboards, and an alert for the specific failure mode. In your answer, cover symptom confirmation, traces and profiles, query plans, cardinality, recent changes, tenant impact, rate limiting, cancellation, rollback, and a permanent prevention mechanism. Question 19. How would you choose between synchronous request handling and asynchronous processing for a backend feature? I keep work synchronous when it is short, predictable, and the client needs an immediate result, such as validating dashboard metadata. I move it to a durable job when it can exceed request deadlines, requires retries, or consumes substantial resources, such as a large export. The asynchronous API should return a job ID, expose status, and define cancellation and failure semantics. Queues add operational complexity, so I would not introduce them without a clear reliability or scalability benefit. Discuss latency expectations, operation duration, user feedback, durability, retries, consistency, resource consumption, cancellation, polling or callbacks, and the complexity cost of introducing a queue. Question 20. How would you investigate and fix a memory leak or steadily increasing memory usage in a Go backend? I would first distinguish a true leak from legitimate cache growth, workload changes, or delayed garbage collection. Heap, allocation, and GoRoutine profiles can reveal retained slices, unclosed response bodies, blocked GoRoutines, or unbounded maps. I would reproduce the trend under controlled load, compare profiles over time, and inspect ownership and cleanup paths. After fixing the cause, I would add bounded cache policies, lifecycle tests, and memory alerts. A lower garbage collection target may help temporarily, but it is not a leak fix. Make sure to cover reproducibility, heap and go routine profiles, allocation trends, retained references, caches, lifecycle ownership, load testing, garbage collection, leak fixes, and regression monitoring. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.